Today's lesson is going to focus on an introduction to organic chemistry and also talk about a process called fractional distillation that is commonly used to isolate organic molecules. We're about to embark on a whole unit in organic chemistry, so it makes sense that we need to nail down the definition of it. So we know the term organic can refer to living matter. It also can refer to a way of farming where you are growing fruits and vegetables with very minimal or no pesticides or herbicides or insecticides. But that definition and that term, or that use of that term, does not apply here in a chemistry class. So when we are talking about organic chemistry in our course, we are talking about molecules and chemicals that are specific to carbon. So our study of organic chemistry is going to look at carbon-based atoms that contain some hydrogen, lots of hydrogen actually, some oxygen, some nitrogen as the primary components of these molecules. So carbon chains form what we call the backbone of organic molecules. All organic chemistry molecules will have either one carbon in their backbone, or maybe they'll have two or three or four, and these carbons will be linked together. They'll be bonded together either in chains or in branches, in ring structures. There's a variety of different ways that they can bond. But the one thing that is true of all organic molecules is that they are covalent. And we know from our grade 11 course, grade 10 and 11 course, covalent molecules are made up of non-metal elements. And as a result, the properties of covalent molecules, which we've studied in grades 10 and 11, apply here as well, because the majority, 99% of organic molecules are still classed as covalents. In order for us to master some aspects of organic chemistry, we have to be aware or mindful of a few things. So a reminder that carbon can form 4 covalent bonds. And we know this already. Carbon sits in group 14. And when he sits in group 14 on the periodic table, we know that that 14, if we lose the 1, refers to 4 valence electrons. So carbon can form 4 bonds around itself. And it will do that in a variety of ways. It might make single bonds, it might make double bonds, it might form itself into a ring structure. Carbon is really, really unique, and it's a unique element in terms of the different ways that it can bond to itself. So we have to remember this, because as we go through and we draw molecules or we're counting bonds, we have to be mindful that it always can make 4 bonds. There are certain carbon substances that are not classed as organic molecules. So here are a few. Carbon monoxide, not organic. Carbon dioxide, not organic. And then anything that is ionic with a carbon. So here's an example of sodium hydrogen carbonate. That's baking soda. And there's carbon in it, but that doesn't mean it's an organic molecule. Organic molecules will have carbon as the backbone with hydrogens in it. And typically there'll be more than one carbon that is bonded to itself. So there are millions and millions of organic compounds. There's over 10 million organic compounds that exist. And what we will do in our course is we're going to be classifying just some of them, not a lot, but based on something called a functional group or the families. We're going to look at about 10 families in this unit. And it's distinctive little features of these molecules that will be identifiable, and they will be similar. We can group them according to the fact that they might have a nitrogen, maybe they'll have an oxygen, maybe they'll have double bonds, and so on. One of the things that you need to do to get comfortable with organic chemistry is get used to seeing organic molecules drawn or represented in a variety of ways. So here's a structure right here. So C3H8 is the molecule or the chemical formula for the molecule propane. And we've all heard of propane, I think. It's the fuel that we use in barbecues. Some of us might use propane to heat our homes. And that is the chemical formula for it. So C3H8. Now, when we are representing this as an organic molecule, remember that carbon has to be the backbone. So what we can do is when we see a formula like this, we can start to expand carbons. So when I see C3, I know that I'm going to have 3 carbons bonded in a row. And remember that every carbon can form 4 bonds. So if I put those valence electrons around each carbon, so there's my 3, the 4th valence electron is actually bonded right here. So I have 1 bond taken up. Those other 3 bonds need to be bonded to something. And what we see is that we have a bunch of hydrogens, and hydrogen has 1 valence electron. And so it would come in and it would bond to each of those valence electrons of carbon. Okay, so we form bonds right there. That middle carbon, okay, so right here has 2 bonds associated with it already. And it doesn't need any more carbons. We know that there's only 3 and that they go in a row. So what would happen here is this carbon would form its last 2 bonds to a hydrogen, okay, or to 2 hydrogens in this case. And then this last carbon has 1 bond formed already to this carbon over here. So what we do is their last remaining valence electrons that need to be bonded will be bonded to hydrogens. And so we'll just replace those valence electrons with a bond. And there you have your formula of C3. So there's 1, 2, 3, and then there are 8 hydrogens surrounding those carbons. That's an 8. Another way of representing these is a lot of times textbooks, I don't love this method, but textbooks sure do. They will isolate every carbon and they will write it out according to how many or what is bonded to that particular carbon. So this carbon right here is bonded to 3 hydrogens. So they'll write it like this, CH3. This carbon right here is bonded to 2 hydrogens, so then they'll say CH2 is next door. And on the end, that last carbon is bonded to 3 hydrogens again, and then they'll show it that way. Okay, so this is what we're seeing in this structure here. And this is very common. You're going to see this format right here many, many times. You can also expand it. Okay, so this is how we kind of started. We started with this displayed formula or the expanded form. And then the other way, and this is actually the preferred way, is to use, it says skeletal formula, but I actually like to call this the line diagram. And this is a favorite of chemists, okay? So this line diagram right here, because it is fast and it's quick and easy to draw. Now, it looks weird. It just looks like maybe an arrowhead to you. But when I see that, I know that that's propane. I know that that's 3 carbons in a row. So what we do is we are saying that every one of these points is a carbon. And we have to draw it sort of going up and down, because if I wanted to draw a line diagram of 3 carbons in a row, I'm going to put my pen down right here. I can't go across, okay, because it gets weird and you don't really know, like what if I had 4 carbons in a row or 5 or 6? It starts to get weird and you're not sure how many carbons are in that particular line when you're going straight across. But if you put your pen or your pencil down and you say, okay, this is carbon 1, and then you move up to carbon 2 and then down to carbon 3, then we know that each of these points, okay, and they might keep going, okay, something like this. Each of those points represents a carbon. And you'll notice the absence of hydrogen, no hydrogen, because it is implied that hydrogen is always bonded to carbon. If a different element is bonded to carbon, we would show that. Okay, so if there was an oxygen, we would show the oxygen. If it was a nitrogen, we would show it. A common way to obtain organic molecules is through a process called fractional distillation. And typically, this is used with crude oil. So you'll find organic molecules naturally. They occur in living things. They occur in plants and trees and herbs and things like that. But crude oil, because it is a source of fossil fuels from thousands and thousands of years, there are all kinds of organic molecules present in it. So when they obtain crude oil, they will pump it out of the ground, and then they will send it off to refineries. And when they send it off to the refineries, the crude oil will enter into a fractional distillation tower. And the first step is to heat the crude oil to a certain temperature. So, right around here, it's saying it's about 600 degrees C. At 600 degrees C, a lot of the crude oil components will boil. So they will vaporize and go into the gas state. And then what they do is they float up in the gas phase through the fractional tower. And as we go up the tower, okay, the temperature is going to get cooler. So the temperature will decrease because the heat source is down here at the bottom of the tower. So as the temperature lowers, and you can see that, we start off here at 600 degrees C, and then they're showing you 270, 170, 70, all the way up to 20. As the temperature cools, these molecules will hit their condensation point. So they'll turn from a gas into a liquid. And the easiest molecule to think about in terms of this is water. So you know that at 600 degrees C, water is going to go into the gas phase because water's boiling point is 100 degrees C. And water would exist as a gas all the way through the tower until it hits around 100 degrees C, and then it would condense into a liquid. So when these molecules condense into their liquids, this is what these little tubes or these pipes are showing, is that they will take those liquid portions off, and then they'll refine them, purify them, and then use them for whatever they need. The smallest carbon molecules, so you'll see here, carbons 1 to 4, will have the highest boiling points. Lowest boiling points. Things that have larger numbers of carbons, so 14 to 20 or 20 to 50, will have higher boiling points. And some of them don't even boil at all. So down here, okay, when they first heat it, things like tar, asphalt, coke, okay, those are compounds that won't even boil, and they'll be like a sludge that they'll take them off and then they'll refine them. And tar and asphalt are used on roads. Coke is not the drink, it's not the drug. It is a form of carbon that they use to make steel. Okay, so they mix coke with iron and then they make steel. So the fractional distillation column, the main points here is that they separate molecules based on boiling points. And when they are separating the molecules, the smaller molecules have a lower boiling point. Okay, and we'll talk more about that when we get into dispersion forces.